everybody. Hi, my name is Charina Chou. Thank you. I'm here from Google. I'm going to share a bit about our perspectives on quantum computing, some recent progress. At Google, the core of the company is computing, right? Google believes in classical computing. We use it day in and day out for very hard problems. And we continue to try to push the boundaries of classical computing, right? With machine learning methods and new tailored chips and other kinds of techniques. At the same time, we recognize that there's entire classes of problems that we won't be able to solve with classical computing, right? We've got to go to quantum computing. And that's the reason this is a very important effort for the company. I put this as the title of my talk, and I also just wanted to underscore it here. The mission of Google Quantum AI is to build a useful quantum computer. What we mean by useful, and this was mentioned in some earlier talks as well, is really a quantum computer that can be used to solve hard problems that can't be solved by a classical computer, right? Hard and important problems. The mission is just 6 words, right? To build a useful quantum computer, but it's very challenging. Along the way towards this ultimate goal of a useful, error-corrected quantum computer, we've identified a number of milestones. Just talk through them briefly, right? Things that we can try to achieve on the path to an ultimately useful quantum computer. The first milestone, milestone 1, we call beyond classical. The first demonstration, any demonstration of some experiment where we are able to show that a quantum computer can solve something that classical computers cannot solve. Milestone 2, the first logical qubit prototype. Milestone 3, a long-lived logical qubit, right? That can be used for actually algorithmically relevant problems. Milestone 4, a tileable module, so looking at creating a logical gate. Milestone 5, engineering scale-up. And then ultimately, milestone 6, an error-corrected quantum computer. And you can see in orange roughly the order of magnitude of a number of physical qubits that we believe is necessary to achieve that milestone. At Google, our team has been able to achieve the first 2 milestones, right? We're making steady progress. I think many people in the audience know we're using superconducting qubit systems. Of course, we're always keeping our eyes open, looking at what others are doing in the field, open to learning from others and adjusting. This is a long-term project, right? It's not going to happen quickly, but we do believe we're making steady progress and have very key milestones to track against. I'll spend a little bit of time just to talk in detail about some of the early milestones, milestone 1 and milestone 2, and then some of our thinking as we try to make our way towards milestone 3. Milestone 1, some of you may have seen this figure before. We call this, again, our milestone to go beyond classical computing. In this case, we were looking not for, the ability to solve all quantum computing problems. We really just wanted to look at one. Could we do one problem where a quantum computer is able to solve something that is intractable on a classical computer? We were able to use random circuit sampling, so you can think of this, really we looked at it as a toy proof of concept problem, right? Where we are able to demonstrate and run a random circuit. Just to give a couple of pointers on this slide, you can see, I guess, maybe look first at the inset. This is a schematic of the chip that we used and circuit that we used. You can see actually that the chip we used is 53 superconducting qubits. And then look at the axes on this plot. The x-axis is number of cycles. You can think about this as the depth of the circuit. And then the y-axis we have is a cross-entropy benchmarking fidelity, so some measure of the error. You can think about this. And as you look at this plot, right, this is data from the quantum regime. You can see as we go to increasing number of cycles, go to increasing depth, increasing circuit complexity. We do see, of course, that we get increasing error, but we are able to calculate some percent of what we are looking for. And the corresponding time that it would take classically for the 20 number of cycles is about 10,000 years on a million cores. And this is something that we know is this was a moment, right? As time goes on, classical computing continues to improve. We also know that quantum computing continues to improve. We believe that this task is exponential with respect to circuit complexity, and so we're continuing to work on this. We do believe you'll continue to see quantum advantage on this type of task. Milestone 2, which I mentioned, suppressing quantum errors. I think everybody in this room knows that the current errors that we see today with physical qubits are just not going to cut it for the real types of problems that we want to solve. In this project, we actually released results in arXiv midsummer, and this is going to be published early next year. You can look at this. I guess there's a couple things to notice in this plot as well. First thing, take a look at the inset. We've gone from 53 superconducting qubits in the milestone 1 experiment to 72 qubits in this case. One of the things that we really wanted to identify and kind of solve, have a proof of concept, is how can we actually start to reduce the error that we have in our chips. Something that people have talked about is, well, you can encode a logical qubit as you go to more and more physical qubits. That's great, right? You can have some kind of duplication, and that can help to mitigate errors. At the same time, we all know that as you add more and more physical qubits, you also introduce more error into the system. So what we were able to do in this case, here you see code distance on the x-axis. You can think about this also as a proxy for looking at the number of qubits in the chip, the quantity. And then on the y-axis, logical error rate per cycle. So of course, as you go to more and more complexity, you want to be able to get lower error rates per cycle. In this work, for the first time, we demonstrated as we go to larger code distance, so take a look at the surface code black data points. As we go to larger code distance, so from code distance 3 to code distance 5, we do see a modest ability to go to better performance, right? Better quality, lower logical error rates per cycle. And this is quite modest, but it was really quite a feat for the team to be able to push the number of qubits in our chip, and then also to demonstrate we were able to make the error rate go down. If you look at the blue dots, those data points are the repetition code. So again, just looking at 1D error correction. So, we do need 2D for actual quantum algorithms. But this was a way for us to demonstrate and test and see what errors are in our system, but also show proof of concept. In 1D, we are able to show with increasing code distance that we can go to lower logical error rates per cycle and actually get down to rates that are meaningful for tough calculations. I mentioned our number of milestones on the way to the ultimate goal of a useful quantum computer. The next milestone that we're working towards as a team, we call it milestone 3. It is a long-lived logical qubit. We believe that we have a shot at this as early as 2025. I think there was an earlier talk around it's hard to predict a lot of these things, and major developments in certain types of research may speed up or slow down the work, but we do believe that we have a shot as early as 2025. You can take a look at this plot, similar axes as the last plot. The y-axis, you've got code distance. Again, you can see a corresponding number of qubits on the top x-axis. And then on the y-axis, you have logical error rate per cycle again. And the gray line, you can see I've labeled that with milestone 2. Those were the results that I just talked about, where we see with increasing code distance from 3 to 5, we were able to get slightly improved logical error rate per cycle. Ultimately, we all know that we've got to get to error rates per cycle that are meaningful for the tough types of algorithms we want to run. We believe that's on the order of about 10 to the minus 6 logical error rate per cycle. So you can see that in the blue horizontal line. And this is a rough plot that outlines our plans. You see milestone 2, where we'd like to get to ultimately is with milestone 3, performance at or below 10 to the minus 6 logical error rate per cycle. So you can see a number of lines plotted here. We've got in the legend lambda, which is some measure of the slope, our ability to go down in error with increasing code distance. And ultimately, we are trying to get to roughly about lambda equals 4. You can see that this is about code distance 17 to get within the 10 to the minus 6 logical error rate per cycle regime. And this is something that we're working hard to do, right? To do this, we're going to have to improve on 2 axes, right? Again, this was talked about earlier today, both quantity of qubits as well as quality of qubits. We believe that we've got some early ideas on how to get there. We're working hard to do it. So why? I think everybody is congregated at this conference because we're interested in quantum computing, because we believe there's some potential, some promise here. At Google, right, there's a lot of things that we are hopeful for about quantum computing. I will say one topic that we are very excited about is this idea of simulation, right? The ability to simulate chemicals and solid state materials and more. And you can see here, for example, right, classical simulation looking at CPU time, you've got methane, ethane, propane, roughly taking on the order of seconds, minutes, and days, respectively, using CPUs to solve the electronic structure of those molecules. As you go to larger molecules, so molecules that are important for catalysis, for example, or ultimately solid state, which we all know is important for batteries and other types of applications like that, it's actually intractable to solve that electronic structure with a classical simulation. With quantum simulation, of course, looking at the number of physical qubits, we do see a lot of promise here. Again, we're in this early regime, right, on the order of 100 physical qubits. We're looking to continue pushing that, and we do believe that there are promising applications as we go to higher numbers of physical qubits, and then also you see, of course, the modifier with QEC, with quantum error correction. We're going to need that, of course, to be able to start simulating some of these more challenging systems. And then I did want to note here, it's not just simulation, right? Everybody gets excited about simulation. We're very much hopeful in that area, but we do see already a number of promising opportunities for non-simulation applications. So things like certified randomness. I mentioned random circuit sampling in our milestone 1 experiment. There are opportunities here, even in the regime that we are at now. And also, we welcome plenty of good ideas. Anybody that's got thoughts, we do look forward to hearing from anybody with thoughts in this area. As we go to larger systems, we do see some promising potential applications, again, non-simulation for topological data analysis, quantum machine learning, and then, of course, as you go to larger and larger systems, ultimately cryptography. So I wanted to share some recent advances in applications from the team. I will point out, importantly, all of this work, a lot of the work that we do and all of the work that's presented here on the slide is done in collaboration with many partners in academia and in industry. We believe that collaboration is critical to continuing to make progress in the field. So you can look at the papers that are represented here. Again, this is just a snapshot. There are many more even from this year in 2022. You can see the full set on our website, quantumai.google. But you can see just a couple highlights. And the first 4 that are cascaded here on the slide, these are actually experiments that are theory as well as experiments, physical experiments done on our quantum processors in the lab. The first, formation of robust bound states of interacting photons. This was experimental demonstration that these bound states do exist. The second, noise-resilient Majorana edge modes. This was an ability to explore actually some of these symmetry-protected 1D edge modes and show that in some cases they are resilient to noise. The third, quantum advantage in learning from experiments. This paper found that there are some classes of systems, for example, physical systems predictions and other types of important systems, where you do get a quantum advantage using a quantum processor. You can learn from exponentially fewer experiments, from exponentially fewer data points than you can using the corresponding classical computer. The fourth one, unbiasing fermionic quantum Monte Carlo. This is a paper that combines quantum Monte Carlo with quantum computation for major chemical simulations. Actually, it was able to simulate systems of up to 120 orbitals. To date, this is the largest chemical simulation that we've seen using a quantum computer. And actually, we're able to get results that are roughly on the order of state-of-the-art with classical systems. And then this last paper that's listed on the slide, resource estimation to assess electronic structure of cytochrome P450. This is a theory paper, again, done in collaboration to look at and assess the classical and the quantum resources that would be needed to calculate, for example, electronic structure of pharmaceutically relevant molecules. This case, the cytochrome P450 superfamily of enzymes. And the findings here were actually the number of classical resources that are going to be needed to really assess the electronic structure are enormous. They're quite large. And so this is a great example of a place where quantum computing really can have an advantage. I mentioned collaborators on the last slide. Collaboration is absolutely critical. We do think that actually, as you go to more and more people that are working in the field, that are thinking about these problems, that are equipped to, bring their own ideas to bear, you're going to get more progress. We'll all benefit from that progress in the field. On the left, you see CIRC 1.0. This is our open source framework for programming quantum computers. This is work done with the input of hundreds of contributors from Google, from other industry, collaborators from academia over the last 4+ years. And when we first started, we had only a couple of qubits and a couple of quantum gates, and obviously things have really progressed since then. We've got a number of new features. We do think this is important, right? We're using this completely internally at our company. We are also seeing lots of open source contributors using this, building libraries on top of it. And this is also supported by a number of quantum cloud providers. On the right, you've got the quantum virtual machine. The experiments I showed on the last slide were actual experiments run on our quantum processor. This is an emulation of Google quantum processors, right? It says no queues, no need to wait in line, but you can try it out. You can get started instantly in Colab. Please do check out these tools. We welcome all of your feedback. Look forward to ways to continue to improve and also ways to see how people are using them. If you're interested to become part of the team, please do come chat with us. I see my colleagues Kevin and also Nick there in the back. We'll be here along with our couple of other teammates over the next few days. Love to hear from you. Team is the best part of working on quantum at Google, and we've got lots of opportunities for collaborations as well as positions on team. I'll just leave with this last slide. It's an image from our lab in Santa Barbara. We think it's beautiful. You can see gorgeous artwork, and we also have a lot of cryostats in this lab. We call it sometimes our cathedral to quantum computing. You've got a quote on the slide from Richard Feynman, of course. By golly, it's a wonderful problem because it doesn't look so easy. It's really hard, but we feel super privileged to get to work on this, and look forward to hearing from you all. Thanks.
Okay, we have a minute or two for questions. Any questions out there?
Hello, thank you very much for your presentation. I wanted to ask about the milestones that you talked about, both in the context of increasing the number of physical qubits and simultaneously also reducing the errors. So when you increase the number of physical qubits, you expect to have increasing amount of errors, right? So how do you hope to increase the number of qubits and reduce the error simultaneously in one of your milestones that you showed? Thank you.
Yeah, that's a really important question. I think there's a lot of things that we're looking at. In some ways, we're looking, I guess, a couple of different things I can mention, and then happy to chat in more detail after the talk too. As you increase number of physical qubits, one of the things that you do is also increase redundancy. So you can accommodate for some errors that were in single physical qubits. You can now start to use that to compensate for the errors. So that's one way that we're looking at it. We're also looking at improvements actually both across the board, right? In things like T1, T2 yields, our gate errors, all of that. There's a lot of techniques that we're trying and looking at different materials as well, but that's another element. And then the third thing that I'll just mention here, and we've got a fantastic team working on quantum error correction code. We do think that there's continued opportunities to try to improve, to move faster, and maybe this can help contribute as well.
There's time for one last question. Any more?
Hi, thanks. That was a really great talk. I really enjoyed it. I just wondered if you might be able to give us any kind of an idea about how you're thinking of approaching some of the scale challenges in getting to 1,000 qubits, like modularity and networking, or is that something you're still not talking about?
Sorry, what would scale up challenges?
Yeah, challenges of scaling like modularity and networking to get to your M3.
Yeah, it's really interesting. So, actually, if you look at this slide that I showed on our milestones, we talk about milestone 1, milestone 2, and then to get to milestone 3, we do see this as one long-lived logical qubit. I didn't mention this, but we have on top of that little graphic, physics de-risked. We do think right now there are still a number of open scientific questions about how you get to one long-lived logical qubit, right? What do we need for T1, T2 times? What do we need for yield? A number of other questions. So these are a lot of scientific questions we're trying to solve. We're also partnering with others. We do think once we're able to get to that, big question again, but as early, as 2025, maybe that's our first shot. We think that being able to tile to get to milestones 4, 5, and 6 actually will be relatively, I don't want to say simple, but we'll have taken a lot of the challenging physics out of it, and it'll be a matter of making sure we've got the right cryostat systems and others to just put them all together.